So now let's figure out how valence atomic orbitals overlap in space to produce molecular orbitals, particularly for second row homonuclear diatomic molecules. So the word homonuclear just means that the diatomic molecules are composed of the same atom. So we're really focusing on the second row of the periodic table here and just the nonmetals really in that row. So it's a fairly limited number of molecules that we have to consider going across the second row of the periodic table. I would like to do an example for diatomic boron, B2. Okay, that's pretty much the first one. When we're considering how valence atomic orbitals overlap to produce molecular orbitals, we have to define what the valence atomic orbitals are. It's very important to note that only the valence atomic orbitals are going to contribute to molecular orbitals because you need to have some overlap. So the core orbitals, in this case the 1s orbital, is not important. The valence orbitals for each boron are going to be 2s rather, and then the three 2p orbitals, which I'm going to call 2px, 2py, and 2pz, just lying along the different axes of three-dimensional Cartesian coordinates. So I want to imagine what happens when we add together the atomic orbitals that have similar energies. So we know that the 2s orbital is lower in energy than the 3 2p orbitals. So the 2s orbitals are going to be the ones that combine with each other. And the 2s orbitals are spherical. And if I imagine kind of doing a linear combination, just like I did before for the hydrogen molecule, just adding two 2s orbitals together, one for each boron, along some internuclear axis, if they are the same phase, I'm going to get constructive interference. So that's going to give me a sigma type of interaction. And I'm going to give it a little subscript 2s to indicate that this sigma molecular orbital was created from 2s atomic orbitals. Now, you know with linear combinations that if I add them together, I also need to subtract one from the other. So I can do that mathematically by just switching the phase of one of them. Now, what happens when I bring those two together is the opposite phases are going to destructively interfere. So I'm going to be left with these kind of shrunken lobes along the bonding axis. There's my bonding axis. And then this node in between the nuclei. So this kind of nodal plane perpendicular to the bonding axis. So that's that destabilizing anti-bonding interaction. So I'm going to call this sigma star, and I'm also going to give it that 2s subscript to indicate that that anti-bonding orbital arises from the 2s atomic orbitals. So that takes care of the overlap of the 2s orbitals. Now I need to think about what happens when the 2px, 2py, and 2pz orbitals on the borons overlap. And if they're going to do so constructively, destructively, or what, or both. And of course, the answer is both. So 2px can interact with 2px. And if you recall, the 2p orbital looks like a set of dumbbells. And I'm gonna use signs once again to indicate the phase. So I'm gonna be adding together two 2px orbitals that look kind of like this. And x, I'm just assuming that the horizontal axis is the x-axis. So if those two approach each other and start to overlap in the middle, this area here and here, these are going to cancel each other out because they're oppositely phased. So that means that I'm going to get this cancellation and this shrinking of those lobes in the middle. And I'm going to get a node in between where I have full cancellation. And, oops, that's the wrong phase. So let me just erase that for a second. I should have a negative there because that's going to be the third lobe from the left. And then I'm going to have this positive here. So this is a very destabilizing interaction. And because that node is created between the nuclei, this is an anti-bonding interaction. The electron density is along the bonding axis, so it's a sigma interaction, but it's sigma star because that node was created between the nuclei. So I'm going to call this sigma star and give it a 2p subscript to indicate that it comes from the overlap of two 2p orbitals. But whenever I add two orbitals together, I also have to do the opposite. I also have to subtract one from the other. So I want to take 2px and subtract 2px from it. And another way of saying that is that I'm gonna add them together but flip the sign of the second one. So it looks like this. So you can imagine now that when this lobe starts overlapping with this lobe, they are going to constructively interfere as I am adding them together. Okay, so I'm adding these two together. That constructive interference is going to give me a nice enhanced region of electron density between the nuclei. So the resulting molecular orbital is going to look like this, and that's a very stabilizing bonding interaction. And so I'm going to call that sigma 2p to indicate that that molecular orbital comes from the overlap of 2p orbitals. So the overlap of 2p orbitals gives rise to a sigma and a sigma star molecular orbital, two molecular orbitals, one bonding and one anti-bonding. Now let's think about what happens if I add 2py to 2py. So I'm going to define y as the horizontal axis, and I'm going to imagine that I'm adding together two dumbbells with opposite phase. So I'm going to say that they are looking like this. I'm going to add these two together. So imagine what happens when these start to overlap. You're going to have this one come into contact with this one, and they're going to constructively interfere and meld together. This one on the bottom, this one is going to constructively interfere with this one, and they're going to meld together. So the result is going to be I have this constructive interference, and I'm going to have regions of interaction above and below the bonding axis. So imagine my nuclei are here. Because the regions of electron density or orbital density are above and below the bonding axis, that's called a pi interaction. And I'm going to call it pi 2p to indicate that the pi interaction comes from the overlap of 2p orbitals. Of course, the linear combination is not complete until I also do the subtraction. So I want to subtract 2py from 2py. And a way I can represent that mathematically is just by switching the phase on one of them. So I'm going to switch the phase there. And I'm going to have destructive interference now. So I'm going to have a new node created where I am canceling out the orbital density and producing a nodal plane that both incorporates the two nuclei and that divides the two nuclei. So two nodal planes are produced from that overlap. That, of course, is an anti-bonding interaction. So I'm going to call it pi star, and I'm going to give it a 2p subscript. It's pi because it's above and below the bonding axis, the overlap. It's star because it's anti-bonding. I'm creating a new node that separates the nuclei. And it's 2p because it comes from the overlap of two 2p orbitals. Now, I could also draw the combination. I won't take the time to draw it here because it's the same, but the combination of the two 2pz orbitals on boron would give another set of pi and pi star molecular orbitals. So there are this up here, this business up here actually happens twice, because I would also have it happening in the z plane to give yet another set of pi and pi star molecular orbitals. So those are going to be the molecular orbitals for any second row homonuclear diatomic.